All right. So like I said yesterday, there are essentially 4 variables that define a substance, and this is especially important for gases. And those 4 variables are the volume, how much we have, the temperature, what temperature that substance is at, the pressure, under what pressure it is or what pressure is it existing at, and then how much of the substance that we're dealing with, which is N, the number of moles. We can easily measure volume. Temperature, we talked about temperature yesterday. We now know that temperature has to do with the speed at which the particles are moving and how whether they're vibrating, translating, or rotating. And we still need to finish our discussion on pressure. And yesterday we got to the point where we talked about how the pressure is the force per unit area, and we talked a little bit about how small a pascal of pressure is, I believe, right? Did we talk about spreading that little mass over that meter squared? And so a pascal is really a tiny little bit of pressure. We also talked about what causes gas pressure, and gas pressure is caused when the particles of a gas, so the molecules or atoms, I guess you could have atomic gases, strike the container, and as they strike the surface of the container, that little contact applies a small force, and that little force exerts a small pressure. And if we could sum up all of those little collisions, then we would have what we call the pressure. And then I asked you to imagine dopey flies, I believe, right? We finished off talking about the dopey flies. So if you could fill a bag with a bunch of flies that were just flying all in, just only in straight lines, and the only way they would change direction is if they bounced off the inner surface of the bag. If you filled that bag with flies, then you'd have so many flies striking the inner surface of that bag that bag would be extended out, because there would always be something in contact with the surface to push it out, all right? And that's what pressure is. So if I have a little balloon here, and I looked at the little balloon yesterday, and I'll blow up the tiny little balloon here. So this little balloon is maintaining its shape because the gas particles are moving so quickly and striking the inner surface of the balloon that it's pushing that balloon out and causing it to fill and maintain the shape. That's actually quite an amazing thing if you think about it. This rubber is quite an elastic substance. It really wants to pull back in. But it's only the motion of molecules that are causing that balloon to have the shape that it has. Molecules are very light. So there's got to be a couple of things that can overcome the stretchiness of this balloon. There's got to be a lot of particles in there, number one, to have so many collisions to push it out against it. And they've got to be moving fairly fast. So we've got some fairly high-speed molecules, and we've got a lot of them striking this balloon to cause this elastic substance to be pushed out in this particular way. All right? Yep?
What happens when the balloon, like when you tie it and it starts to get flat?
When you tie it and it starts to get flat, it probably means that there's some gas actually leaving the balloon. The rubber is actually quite porous. It's more porous than you'd think. If you have helium, the particles are so small, they actually leave quite easily. They just sneak through the rubber, and they just get through the spaces of the molecules in the rubber, and they just leave. So you're actually having less gas in it. So you're losing molecules, and that's why it gets smaller. All right? So you actually have some of the gas leaving. Yeah. That's why if you purchase balloons, like say for a party at a flower shop or something, and you want those balloons to last a little longer, what they will actually do is they'll put a liquid inside the balloon. I don't know if you've ever seen them do that. They've got a little pump thing, and they put something in the balloon, and then they'll rub the interior of the balloon, and then they'll fill it up. And that's another polymer. That's another type of plastic which coats the inside of the balloon, which makes it less porous for the helium to get out, and they'll last a little longer. So there's actually little holes in that rubber, and they do slowly work their way out. So they lose the air. Okay, so we didn't have this yesterday. Did we put that up? Excellent. The SI unit for pressure is the kilopascal. Actually, it is the pascal, but we use in this course the kilopascal, and that's because a pascal is so small. I talked about that yesterday. If we had a meter squared and I took a 100-gram mass and could smear it over that meter squared, there would be that would be a pascal of pressure. If I could put my hand under it, and I would hardly feel anything. So we need to talk in terms of thousands of pascals, kilopascals, in order to really have any pressure, any significant amount of pressure. Okay, so some very important temperatures and pressures that we will be encountering in this course. So chemists have chosen temperatures and pressures that are very important to chemists and have kind of set them as special or standard temperatures and pressures. And we use these temperature and pressures in various situations and calculations. Standard temperature and pressure, STP. Again, standard temperature and pressure. STP has been defined as being two important values that kind of get their values in different ways. 0 degrees Celsius, that's a fairly obvious number and why it was chosen. Ice, water, transition, 0 degrees Celsius. 101.3 kilopascals. You might think that that's an odd number to choose as a special pressure, but that pressure has been determined to be the average of the atmospheric pressure that is found at sea level, so at a particular altitude, and that's defined at sea level, all over the world. So if we were to take that pressure of the atmosphere above us and measure that at different places in the world and take an average of all of those pressures, we end up with this number of 101.3 kilopascals. All right? Now let's talk a little bit about atmospheric pressure just for a moment before I talk about the other pressures and temperatures. Here, let's turn this on and let's start up the notebook. And let's see if it will start up. Oh, the speed of the computer system. Oh, so exciting. All right. So essentially, right, can I do a shape here? Let's draw an Earth. That's not an Earth. I can't draw shapes with this device. Nope. So we get to draw on it. Let's draw an Earth. Earth, right there. Okay? And I'll draw myself on the Earth. There I am, on the Earth. And above the Earth, we obviously have atmosphere. I'll just put some air around the Earth. It's horrendous, but that's the air. That's the air around the Earth. And above us, there's always a column of air, whether we talk about us or, over top of a surface like a football field. It doesn't make any difference. But above us, there's always a column of air. And that air gets thinner as you go higher up, right? This is thin air, and down here it's essentially thick air, all right? It's essentially thick. And gravity pulls down on that air, Fg. That's why the air sticks around on the surface of the Earth, because gravity is pulling it down. And that means if gravity is pulling down on the air, then that air has weight, all right? Gravity is weight, by the way. What's the weight of the air above us? Well, we can measure that weight by reading the pressure. And the pressure, on average, at the surface of the Earth, that pressure is about 101.3 kilopascals, all right? Now, 101.3 kilopascals. If we get rid of the kilo, that's essentially 101, and then I move the decimal place over 300 pascals, right? And if we think about what a pascal is, remember yesterday, 1 pascal is equal to 1 Newton over 1 meter squared. Which means if, let's say that this was a meter squared. Let's say right here, that area above my head is about a meter squared. If that's a meter squared right there, if I've got 1 meter squared right there, then that means instead of 101,300 pascals, there's actually 101,300 newtons of air over that meter over my head, right? If I measured a meter over my head, that much, that's not too bad, it's about a meter. Then right now, the air above me has a weight of 101,000 newtons. 101,000 newtons. Now, a newton is not very much, but 100,000 newtons is a lot. Right here, I have my 1 kilogram mass. That's 10 newtons. Right now, above me, even though there's a roof and then there's multiple floors above me, that air pressure comes in and fills the room. I could do this outside. It makes no difference. But right now, there is 101,000 newtons of force being pressed down on my skin, on my shoulders, due to the air above me. That's a big pressure. That's a lot of weight. Now, we don't sense this because humans have evolved in the gravitational field that is down on the surface of the Earth, and we've evolved with this air always around us. So we are just simply accustomed to this huge pressure of the air that's piled up on top of us. But we can sense when we go to an area where there's less pressure. If we get into a plane and we fly to a location that is higher in the air, so let me get my plane here. So here we go. So now I'm flying around up here. There's my plane. It's a horrendous plane. Flying around in my squiggle plane. And now there's only that much air above me. It means that there's less pressure because I don't have to hold up as much air. And right away, my ears tell me, whoa, less pressure, uncomfortable. This is horrendous. I don't like this. I need some gum. Got to chew on that gum. So the pressure equalizes. The reason for that is inside of our middle ear, right? Here's our external ear. Some of them are bigger than others. Don't make fun of my big ears. So here's our external ear. And then the middle ear, which is where the little bones are. I don't know. You realize there's little bones in the middle ear. Somebody taught you that before. And then you've got your inner ear. That middle ear actually has an air space. In your middle ear, there's 3 little bones that connect your eardrum to the sound sensing organ. And there's a little connection from that middle ear, because there's actually air in there. There's actually air behind your eardrum. And there's a little connection to your throat called the eustachian tube. And when you swallow, the eustachian tube opens up, and you hear a little click. Everybody swallow. I heard the click. It's right there. It's right there. Did you hear the click? Did you swallow? You did not. What's your question?
Like when you get swimmers here then, is like the airspace for the water?
Yeah, the water gets into the airspace, and then it ends up infected because it doesn't drain very well. And then, yeah, you get swimmer's ear, right? usually that eustachian tube, which is a tube that goes to your back of your throat, allows the liquid to drain out. But if it doesn't function very well, which maybe means you don't hear the click, then any liquid that gets in there ends up sitting in there, right? And that's why that's why some doctors put tubes in kids' ears, and what they'll do is they put a little tube in the eardrum so that that moisture can get out without it having to go through that eustachian tube, right? And then, of course, you're ridiculed. Hey, you want to go swimming? I don't have my ear plugged like that. I got tubes in my ears. You know how that works. Did you have tubes in your ears, Hannah? Oh, okay. Anyway. All right. In the airplane, though, air gets trapped in there. Eustachian tube is closed. Eardrum is closed. You've got pressure that is the same as being down on the Earth's surface, 101.3 kilopascals. And then you fly up to where there's less pressure, and now your eardrums push out because it's like a balloon. The air inside your ear desperately wants to get out, and so your eardrum gets pushed out, and it's very uncomfortable. So then you chew your gum, you open the eustachian tube, a little bit of that extra air leaves, and you feel comfortable again until when you land. And then now there's less pressure in your ear, your middle ear, and it pushes in, and it's very uncomfortable. And then you chew some more gum, and you open the eustachian tube, and it lets the pressure equalize again, and you feel comfortable again. But we have an incredible amount of air above us that is weighing us down, but we're used to it. We can feel the same idea with a different fluid, like when you go into a swimming pool. You go into a swimming pool, all you got to do is go down by like 10 feet to get the divey thing, the thing you throw in to dive after. You go down 10 feet, and right away you can feel the pressure. Oh, man, this is uncomfortable. I got to get back to the top. Oh, that's better. And that's because water is far more dense than air. So a small change in depth in the fluid of water makes a great pressure difference. Again, the reason you feel the pressure at the bottom of the pool is because you're holding up all the water above you. All the water above you is being pulled down by gravity and impinging pressure on you. So right now, we're at the bottom of a swimming pool of air. We live at the bottom of the ocean of air, all right, just like the creatures in the ocean that crawl along the bottom. And we're used to the pressure of the air above us. It's literally the weight of the air above us. Yep.
So if you were to go in a submarine,
Yep.
go way deep,
Oh, yeah.
would there, like, since that pressure is so intense, would there be something in the submarine
To have to push that back out? Well, the structure of the submarine itself is going to prevent the pressure of the water from changing the pressure of the air inside the submarine. Actually, the air is pushing out a little bit. Actually, no, sorry. The air pressure is going to be a lot less. So we're going to have this incredible push in from the water, and so the structure has to do the job of holding it out. And if that structure were to collapse in, your ears would sense an increase in pressure because the structure would be failing. If the structure was failing, sore eardrums would be the least of your worries at the bottom of the ocean. But you would sense that just before the water rushed in and you died a horrific death. But the structure of the submarine is what's going to keep that pressure tolerable inside it. All right? Okay. Again, just another calculation just to put it into some perspective. If we assume that G is equal to 10 newtons per kilogram, we all know as physicists it's 9.81. I know, but let's just make it 10 for ease of calculation. That means if we are being weighed down by 101,300 newtons, if I divide that by 10 newtons per kilogram, then I end up with taking one of these zeros away, 10130. 10,000 kilograms of air exist above us. That's what we're holding up. We literally hold up 10,000 kilograms of air every day. So if somebody says, get off the couch, quit playing video games, go do some exercising, you can say, are you kidding me? I'm holding up 10,000 kilograms of air right now as I speak. I'm doing workout all the time. Oh, 10,000 kilograms. No problem. Which really doesn't mean much because we're used to that 10,000 kilograms of air being on us. But there literally is. There's 10,000 kilograms of air above us. Yes?
But if you're in a house, is the house holding you up?
No, because houses are not airtight. As soon as you open a window, even you don't even have to open a window because air gets in and out of a house all the time, that weight of the air squeezes into the house. It's just being pushed into the house. So that full weight of the air is also inside the house as well.
So the amount of pressure from the earth out to the atmosphere is the same as from your shoulders to the ceiling?
No, it's nothing like that. No. If you were to take your house and put it at the bottom of the ocean, right? Let's say you put it at the bottom of the ocean, you would not be able to necessarily just say, oh, I don't have to worry about the water rushing in because the roof's just going to hold the water up. I can even open the windows because that water on the side isn't being pushed down. So I'll just open the window, the water will be, that type of thing. That's cool. I live underneath the ocean. I can open the window. There goes a fish. Grab a fish out, out of the water. You can't do that because it's a fluid. As soon as you opened it, the pressure from that water that's beside the window would rush into the house. That's exactly what's happening here in the air. That would be the same as saying in your house, because the roof is holding up the air, there should be no air in the house, which means you would die a horrific death of some kind of no oxygen. Everybody house dies because the air couldn't make it in the house. You see what I mean? So the pressure of the air beside it pushes that same pressure inside the house, which means you're still being impinged on by the same pressure of the air that's to the outside. So yeah, right now, even in this building, we are being subjected to about 10,000 kilograms of air pressure. Yes. Okay? All right. So that's where this number comes from. This number, 101.3 kilopascals, is the average air pressure over the surface of the earth. And that's an important thing. That's an important number because that's the way we exist. We exist in that air pressure. Same with the molecules, same with the water, same with the ice. So if we want to study the substances on the planet Earth, then we need to be worried about that pressure. All right? 0 degrees Celsius, that's where water melts, freezes. That's important as well. SATP, that stands for standard ambient temperature and pressure. Also a very important temperature and pressure. These have been decided by chemists as being important numbers pertaining to laboratory conditions. In a laboratory, the temperature is usually around 25 degrees. It's a little warmer than what we consider room temperature, 23. And that's because there are usually motors running and maybe there's a refrigerator to house some materials, or there's pumps going, or you're running a Bunsen burner, or you're doing this or doing that, which tend to generate heat. So laboratories tend to be a little warmer than regular rooms, 25 degrees Celsius. The pressure in a laboratory also tends to be a little lower than atmospheric pressure because most laboratories have venting fans that suck air out of the lab and then vent it to the atmosphere. So if you're working with chemicals that are producing gases that you don't want to be breathing in, right? You have fume hoods that are drawing that air out of the building and then out into the air. So usually the sucking of the air out of the laboratory brings the pressure down a little bit. So standard ambient temperature and pressure basically indicate laboratory conditions. When we look at our periodic table and we look at all of those states, liquids, solids, gases, those particular states are what you would see under standard ambient temperature and pressure. So we define our states on the periodic table, what we would see in laboratory conditions. Okay? So one is more atmospheric, right? Out in the open, what you would see. The other one is more laboratory conditions. On the periodic table, it's SATP. They're what we would see under laboratory conditions. Okay? Because as soon as you change the temperature and pressure, it changes the way the chemicals behave a little bit. Other units. taking standard pressure and converting it into other pressure units, because we will be using other pressure units in this unit. Here we've got atmospheres. Atmospheres is a unit that astrochemists would use. An astrochemist would be someone who studies the chemistry of materials on other planets, and it essentially is the way we compare our atmospheric pressure to other planetary atmospheric pressure. So we say on Earth we're subjected to 1 atmosphere, but if you went to Jupiter, there would be, hundreds of atmospheres of pressure. If you went to Mars, there's less than 1 atmosphere. If you go to Venus, I think there's something like 7 or 8 atmospheres. So if you went to Venus and stepped out of your spaceship without any protection on, you'd be subjected to 7 times our pressure. Our bodies wouldn't like that. You would not survive, despite the fact that there's no air, and I think there's sulfuric acid in the atmosphere, which would burn your skin. But, the pressure wouldn't be great for you either. So just not a good idea. Step out of your spaceship on the planet Venus. All right? So atmosphere is an astronomical unit that we use to compare the pressures on other planets. 760 millimeters of mercury. That has to do with the way we used to measure pressure. All right? Let me just talk a little bit about the way we used to measure pressure here. Let me add another page right here just for a second. Original barometers were actually made out of columns of mercury, right? If you had a bowl of mercury, right, and this is the way the first barometer was invented by a scientist by the name of Torricelli, which is why our other unit is called Tor. What he did was he simply had a glass tube, right, that he filled with mercury, right? So this is all Hg. And the air pressure would push the mercury up the tube, and the regular pressure the regular height in which it would get to was 760 millimeters. Okay? Now, how did he come up with this idea? This is the way he built the first barometer. Now, we've all done this. As children, we're great scientists. And one of the first experiments you do as a child involves the bathtub and water in the bathtub, right? Bath time. Yeah, great thing in the world. Okay. Not just bath time, though. You got to fill it with cups and with toys and with rubber duckies and all kinds of other things, squirt guns and whatever you want. But it's the cup that's the best toy ever. We've all done this. You take the cup, and then you turn it upside down, and you put it in the water, and then you push it in, and then you lift it out, and it doesn't have any water in it, you notice. That's kind of weird. I can push that in. Where does the water? Why isn't there any water in it? All right, so then you continue to experiment, and you've all done this. So you push it in, and then you try to look inside, and the bubbles come up, right? The bubbles come up. Hey, that's fun. You've all done this, right? And then you pour it on yourself. That's good. But then as you continue to evolve as a scientist, you put it in. That's fun. Bubbles come up. Then you turn it upside down, and then you bring it out, and then it's really heavy. And then when you get it out of the water, all this water comes pouring out. You've all done this, right? Yes, we've all done it. If you haven't, you should try it sometime. So here's what Torricelli did. I'm sure a young Torricelli, Italian, 1700s, in his bathtub. Anyway, he imagined taking the cup, and he then imagined, what if we could extend the cup? What if the cup could be like a really long cup, like a tube, and we could keep sucking that water up? How high could we make that tube if you could have an infinitely long tube? How high could you make it? Would it continually suck up the water? This experiment was tried, actually, in a harbor in Italy somewhere. He organized this, a big glass tube under the harbor, filled it with water, and kept lifting this tube up against a big boat, tied it to a mast. And he had to get to something like 10 or 12 meters high. And when he got to 10 or 12 meters high, the cup couldn't suck the water up anymore. It got to a certain height where the water stopped, but the tube kept going. Couldn't suck up any more water. He got thinking, what's causing the water to go up in the cup in the first place? And it didn't take him long to realize that the pressure of the air is actually pushing the water up the column. And at some point in time, the pressure of the air is not great enough, and it cannot push the water up anymore. And that was the first barometer, the first pressure measuring device. Instead of using water, in order to make his device smaller, he wanted a heavier liquid. Mercury was the heaviest liquid that they knew, and it still is the heaviest liquid. So when he did the same experiment except with mercury in it, he could get the tube to go up 760 millimeters until the mercury couldn't be sucked up anymore. The weight of the mercury was balancing out the pressure of the atmosphere. He put this thing on his desk, and when it was sunny out, right, when the sun came out, that's the sun, all right, then the mercury would go up, and there would be high pressure. And if it was cloudy, so here come the clouds, and then the mercury would go down, and it would be low pressure. And he was able to start doing weather prediction by looking at that change in the level of the mercury in his tube, right? And that's the first barometer. So what do? We now consider this measurement of millimeters of mercury, 760 millimeters of mercury, right? 760 would be 76 centimeters. I guess it's that long, 760 millimeters of mercury, as being an important pressure unit. We also call it torr because Torricelli was the one who invented that, okay? And then we also have pressure measurements like PSI, pounds per square inch. And we use PSI for like regular industrial things. If you're going to pump up your tire in your car, how many PSI? No? About 35. 30 to 35. 30 to 35 PSI results in your tire being pumped up. Okay? Now, just to finish our little note on pressure, we're going to do some conversions here because in the end, we want kilopascals. We're going to be doing some calculations where kilopascals is the important calculation. So we need to be able to convert these to kilopascals. Using the units on the previous page, remember when I first introduced you to conversion factors, if I had an equality, I could easily turn that into a conversion factor. So if I am going to convert atmospheres to kilopascals, then I'm going to create a conversion factor that has me get rid of atmospheres and has me get the unit of kilopascals. I need kPa on the top, and I need atmospheres on the bottom. What numbers am I going to put in here in order to get that to be a true statement? Yep. And 1 on the bottom. And that'll do it. So all we're doing is generating conversion factors. One atmosphere, by the way, is a whole number defined that way. So I'm looking at 3 significant digits here. And Nathan's not here, so we need someone to step up. Yep.
177.
177, and that's kilopascals? Okay. I'm really only going to be wanting to turn it into kilopascals because that's the number that's found in many of our equations. So it's always going to be 101.3 kilopascals on the top. What's going to go on the bottom of this one if I want to convert it? Carissa? Yep, 760 torr. Again, 3 significant digits throughout this. Yep. 86.6 kilopascals. We like it? And the last one, again, 101.3 kilopascals. What's going on the bottom of this one? 14.7? 14.7 PSI. PSI stands for pounds per square inch. And I believe you have that list on your information sheet on your periodic table. Just check to see that it's there. So you really don't have to memorize them, but you do know how to use them. You do need to know how to use them. What do I have here for a number? Taylor seems to be filling in. What do you got? 141? 241 kilopascals. Okay? There is a little question in the book that deals with that.